It's my great pleasure to introduce Nobel laureate and a good friend, Kip Thorne.
Thank you, Anton. It's a real pleasure to be here. I have a very soft spot in my heart for Anton and Micah and Iset and this part of the world. And so I'm really, my wife and I are enormously enjoying being here for a few days. Can we turn the lights down now so we can see the screen better? Can we turn the lights down? Okay, that's great, that's good. Okay. So I'm going to begin by telling you a little bit about how this movie was made. The story begins with Carl Sagan, who was an astrophysicist, but also a filmmaker and himself and a TV star, who was a personal friend of mine. And he called me up in 1980 and said, "There's a woman in Hollywood who would like to have a blind date with you." It's a phrase some of you may know. It's a date where you get together for the evening, although you have never met before. And so we did, and her name was Linda Obst, and she was just starting her career as a movie producer and became a very successful movie producer. She did a number of well-known movies, including Contact with Carl Sagan, for example. And she and I went out on a date, and we found each other very interesting, but the romance did not go anywhere. She was too intense for me, and I was too much of a nerd for her. But we did become very close friends, and 25 years later, in 2005, Linda phoned me up and said, "Would you like to brainstorm with me for a movie?" And I thought about it for about 1 millisecond. And I decided, yes, that would be fun to do a movie with Linda. I'd never been deeply involved in a movie before. And I might be able to inspire people about science through this movie. And so we developed a treatment for the movie that we called Interstellar. And the treatment is a description of the story, of the characters, and in our case, of the science that would be built into this movie from the beginning, tightly integrated into the movie. And that is how this treatment differed from other treatments in Hollywood. And so the following February, Linda brought on board Steven Spielberg to direct the movie. And Steven and I got together. I'm sorry. Woo. I think we have a bit of a problem. That is really remarkable. Never seen that before. It's just... I don't know what... I'm going to... Okay, let me start over again here. There. Okay. Okay. And I said to Stephen when we got together that first time that I would like to do a movie in which there were guidelines that nothing in this film will violate firmly established laws of physics or well-established knowledge of the universe, and speculations about poorly understood physical laws and speculations about the universe will arise from real science. Stephen was enthusiastic to do a movie that way. He had never done a movie in this kind of a manner, so we were off and moving forward. And so Stephen and Linda brought on board in January 2007 Jonathan, or Jonah he's called, Nolan, to be the screenwriter for this movie. And Jonah read many relevant science books, popular science books that I gave to him to give him some background about the science in the movie. And he brainstormed with me for the science in the movie, just as Linda and I had brainstormed together. Between 2008 and 2010, he wrote 3 drafts of the screenplay. But then on June 8, 2010, Steven Spielberg dropped out. Spielberg has a very different style than some other movie makers. He carries along in the early creative phase more movies that he can possibly make. And when he gets to the point of just before pre-production, he makes the decision which movie he will actually make himself, and then he will let you go find somebody else to direct your movie if he doesn't choose it. He chose to make the movie Lincoln, about President Lincoln and the freeing of the slaves, and not to make Interstellar. And so we were left for 2.5 years with no director on this movie. However, Christopher Nolan, the brother of Jonathan, or Jonah Nolan, he had told us very early on that if Spielberg dropped out, he might want to become the director. He knew Spielberg's style. But Christopher Nolan's style was completely different. Christopher Nolan would never commit to a movie until 6 months after he had finished his preceding movie. Then he would look carefully at his options and make a decision. And so he had to finish his movie about the Dark Knight Rises, Batman movie, and he had to finish that off before he made a decision. But he did make a decision then and decided he really did want to do Interstellar. Spielberg said to us at that point, he said, "You got the right director for your movie." And I think it's absolutely true. Spielberg, I had gotten to know him rather well. He had made science fiction movies previously. I don't think Spielberg was anywhere near as enthusiastic about Interstellar as Christopher Nolan. And I, just from working with the two of them, I really am convinced that Christopher Nolan made a much better movie from it than Steven Spielberg would have. Christopher Nolan is interesting. He has a strong science intuition, but it's all based on browsing the web and not having had science training. But he knows a lot about science from browsing the web. He accepted my guidelines, as he said, to the extent they do not get in the way of making a great movie. He was afraid I would play the role of a policeman to tell him what he could do and what he couldn't do. And I was afraid he would take the movie in some crazy direction that was totally violated the science. But as we started to talk with each other, we quickly came to appreciate that we both had the same goals, we both had the same tastes. We really wanted to stick to the science. We really wanted to make a great movie. And this turned into just a fantastically wonderful collaboration. Chris brainstormed with me on the science through 3 more drafts of the screenplay. And the final screenplay then and movie preserved Linda's and my science vision, but they changed the story and the character in major ways. That means that Interstellar is really the Nolan's movie. It's not Linda's and my movie. But the science that is embedded very deeply here is my science tweaked by the Nolan brothers, and some interesting science ideas that the Nolan brothers brought into it as well. I wrote a book about the science of Interstellar. I only decided to write that book while the movie was being filmed. It was already in the filming process. But it seemed to me that this was a tremendous opportunity. And so I spent 4 months writing this book. And it had to be published the same day as the movie was released. But I was not allowed to, and the publisher was not allowed to let the world know that there was a book connected to the movie, because Emma Thomas, Christopher Nolan's wife, who became the lead producer on the movie, she was afraid that if people knew there was a book about the science in the movie, they would think that the movie was too complicated for them to go see. and so they wouldn't go to the movie. And so we published the same day as the movie came out, and only gradually did people become familiar with this book. Now, in what follows, I'm going to label slides by whether the science that is connected to the slide is firm science that we really are quite certain of, or is to some degree speculative. So, for example, on this slide it says an F, so this is firm science. We know what we're talking about. This is really the way the universe behaves. And here I'm talking about the relativity of time, which you see in the movie. So Cooper says to Murph, when I'm in hypersleep or travel near the speed of light or I'm near a black hole, time will change for me. It will run more slowly. When I get back, we'll compare. We might even be the same age, you and me. Imagine that, the slowing of time. And Chris said to me early on, I want that 1 hour on Miller's planet, the water planet, is 7 years back on Earth, 7 years in the Endurance spacecraft up high above the black hole. That gravitational time slowing is so extreme that 7 years up high is 1 hour down on the planet near the black hole. When Chris asked me for this, he said he wanted 1 hour is 7 years. That's a factor of 60,000 slowing of time. I told him immediately, this is not possible. I just know how relativity works. You can't get that much slowing of time. He knew me by then, and he knew that I would have an immediate intuitive reaction to something he proposed, and that I was sometimes wrong. And so he said to me immediately, go do a real calculation and show me that that's true. So I went away, I did a real calculation, and I discovered that I was wrong, and he was right. He could have what he wanted. If Miller's planet is just outside Gargantua's innermost stable circular orbit, and Gargantua does not spin, then the slowing of time is only by about a factor of 2/3, not by a factor of 60,000. But if Gargantua, the black hole, spins very fast, so fast that its angular momentum of spin, divided by the maximum spin the laws of physics would allow it to have, is this much. So it's very nearly to within 1 part in 10 to the 14 in technical language of the maximum. Then this innermost stable circular orbit, the closest the planet can be without falling into the black hole, is so close that it is possible to have the factor of 60,000 slowing of time that Chris wanted. Not very plausible, though, but it's actually possible. And so I said, well, we can go with this, that's fine, because it is possible, and that was sort of the guideline that we had, even though it was not likely to actually occur in the real universe, but at least it was physically possible. Now, there was one problem, a serious problem in this whole process. I was not talking with scientist colleagues about the issues in this film. I should have been. Without talking to scientist colleagues, I missed important things. And the most important thing that I missed, that I should have realized, is that with this much slowing of time, that means that the light that is coming in from a hot disk around the black hole, that light, the photons of light, when they arrive at the planet, they have fallen through a very large amount of gravitational pull, and they will have been shifted to the blue to the point that they are actually hard X-rays, and that's going to be rather unpleasant for the people who go down on the planet. So that's the biggest flaw in the movie, as far as I'm concerned, a flaw that it was my fault for not talking to colleagues and having them point this out to me. Now let me talk about the orbit of Miller's planet then. If I take the black hole Gargantua and I put an equatorial slice through the black hole, then space is warped around the black hole. In fact, the black hole is made from warped space and warped time. And so I can visualize this warping of space in this following way. I take a flat space that is not warped, and then I take that surface and I put it in the flat space so I can see what the warping looks like. We call this flat space the bulk. That's a name that physicists use for this higher dimensional space that is not part of our universe at all. It's a space in which we can think of our universe as embedded. It lives inside that higher dimensional space. Christopher Nolan calls it the fifth dimension because you and I have three space dimensions, north, south, east, west, and up, down. And one time dimension, that's four, and then this is a fifth dimension that's going out of our universe. And so this is that dimension, the bulk going out of our universe. This is the shape of space around the black hole. So if the orbit of the planet Endurance is up here, this is the actual shape of space for a black hole with that fast to spin around that black hole. Miller's planet is down here, and the horizon is down there. The horizon is actually a sphere. This looks like a circle, but I removed one dimension. I'm only talking about the two-dimensional slice through the equator of the black hole. And so each of these circles you think of as actually being a sphere. And Miller's planet is actually relatively far away from the horizon of the black hole, and the Endurance is way a lot farther away. But the circumference of Miller's planet, of the orbit, is almost precisely the same as the circumference of the black hole. Now, in the movie, you see a giant water wave that does not break. By contrast with waves in our ocean, when a wave in our ocean gets this steep, then it curls over and breaks. Let me remind you of what this looks like.
How long for the engines, Case?
A minute or two.
Well, we don't have it. Helmets on! Brandon, co-pilot, you're up. Case, load cabin oxygen through the main thrusters. We're gonna spark.
Roger that.
Locked.
Depressurizing. Engines up!
So why does this wave not break? The answer is that it is a realistic kind of wave, a kind of wave that you don't normally see. But it's called a solitary wave or a soliton. It has a shape, in fact, just like this. It's a little bit exaggerated, but not a lot exaggerated in the movie. And the height to the wave is 5 times higher than the water is deep. I'll return to that in a few minutes. And there is physics that underlies this. This is an example of the fact that this movie really is based on real physics all the way through it. And the physics is that there's something called dispersion, which says that when you have a wave like this, the more gentle parts of the wave will feel the ground beneath the wave more than the sharper parts of the wave. And so it turns out they travel more rapidly, and the sharper parts of the wave travel more slowly, and the wave comes apart. This is called dispersion. The wave disperses as it travels. And that's a fundamental process that always occurs on water waves when the water is not really, really deep. But there's another effect, which is called nonlinearity, which says that the higher part of the wave will travel faster than the lower part of the wave. And that's doing just what the opposite of what the dispersion is. And it turns out that the two effects, the dispersion and this nonlinearity, balance each other out perfectly in a stable sort of a way. This is described in physics or engineering by something called the Korteweg-de Vries equation. And the wave maintains its shape as it travels. In fact, if you have two waves of this sort that travel through each other, they come together, they appear to merge, and then they pass right through, and they regain their original shape and speed. So it's really quite an amazing thing, and that's what's going on in this movie. But the water on the planet is such that the water on the planet needs to be much deeper than what we see in the movie because they're walking around in the water and this wave sweeps over them. And the wave is really high, and so the water has to be a lot deeper than what you see. But that's easily explained. They're on an island, a submerged island, but the wave comes in from much deeper water, and it travels over the island, hardly affected by the island, and keeps going. So what at first appears to be very strange is really in full accord with things that you can do in the laboratory, in fact, that engineers do. And as I remarked, the wave's steepness, which is just as shown here, is slightly exaggerated, but not a lot in the movie. Now, there's something called tidal gravity. I'm going to explain how the wave comes about. Something called tidal gravity, that the moon raises a tide on the Earth's oceans, and that happens because of the following, that the gravitational pull of the moon is stronger on the side of the Earth that's close to the moon than the side that's farther away, because gravity is weaker as you move away from the source of the gravity. And the gravity of the moon points toward the center of the moon, and so there's a slight inward piece of this gravitational pull. But if you're riding on the Earth, you don't notice the part of the gravitational pull that is acting at the center of the Earth. Basically, you're falling freely as you travel on the Earth and the moon and Earth going around each other. You don't feel the average gravitational pull, and so we throw away the average gravitational pull, and you have a gravitational pull that stretches the Earth in this direction and squeezes in that direction. So this is the standard cause of the Earth's ocean tides. Now, there's a formula for this that says the acceleration on the two different sides of the Earth is something called the tidal field. And the important thing I want to point out is it's proportional to the mass of the moon divided by the cube of the distance between the moon and the Earth. And this is the radius of the Earth. So it's, the bigger the Earth is, the stronger this difference in acceleration is. So in the case of Gargantua, you have Miller's planet. It's the Gargantua's tidal field is deforming Miller's planet. And in the movie, it is designed that that Gargantua's tidal field deforms Miller's planet quite a bit, but not so much that it tears Miller's planet apart. So if I look at this then, this is the direction toward Gargantua, or it could be up like it was before. And this is the tidal field, stretching and squeezing it. The tidal field, I'm going to give you some formulas, but I just want to, for this few people here who know these kinds of formulas, I just want to do a little bit of complicated stuff. The tidal field, again, is proportional to the mass of Gargantua divided by the cube, it turns out, not of the distance to Gargantua, but of the circumference of the black hole divided by 2 pi. We can call that a placekeeper for the radius. And the planet is very close to Gargantua. The fact that it's very close to Gargantua means that this distance, or this circumference divided by 2 pi, is approximately this formula. G is the gravitation constant, speed is the speed of light, but it's proportional to the mass of Gargantua. Again, this is for a few people in the audience who would understand this. I put that into this formula, and I get that the tidal field near the horizon, that's stretching and squeezing near the horizon of the black hole, that's stretching and squeezing the planet, scales as 1 over the square of the mass of the black hole. So these are sort of standard formulas for a physicist, but you can go in from that and you can recognize then that the bigger the black hole is, the smaller the tidal field. That's quite strange, but that's the way it goes. And from the fact that it needs to deform the planet noticeably, you can calculate then what the mass of Gargantua is. The mass of the Gargantua turns out to be 100 million times bigger than the sun's mass. 100 million times bigger than the sun. That, in fact, is the mass of the black hole that's in the nearest large galaxy to our own galaxy, the galaxy Andromeda. There's a black hole there, and it is about this mass. So it's not an unusual mass for black holes. And that's what we have chosen for this movie. But that also turns out to mean that their circumference of Gargantua's horizon is the same as the circumference of the Earth's orbit. So Gargantua is the size of the orbit of our Earth around the sun. It also turns out to mean that Gargantua's tidal field, that you might think, well, that's going to stretch and squeeze us. It's like the astronaut falls into a black hole and gets stretched completely, his body stretched, spaghettified, we say. But in fact, with that big a black hole, I told you the tidal field is small for big holes. The Earth's tidal field is, the Gargantua's tidal field is about the same as the Earth's tidal field. So humans don't even notice it. When the humans go down on the Miller's planet, they don't feel this tidal field of the black hole. They're almost at the horizon of the black hole, but they don't feel any stretching and squeezing at all. The planet is stretched and squeezed because it's much bigger than the people are, but the people are not, don't feel any of it. And so how are the waves generated? Well, if Gargantua is down here, you think of this as being the black hole, or the planet is shaped like that. There's a gravitational pull toward Gargantua, and it's pretty obvious the planet is going to swing back and forth like a pendulum under the gravitational pull of Gargantua, because this is sort of like a pendulum. It's elongated. And so you can go in with the formulas that you get from the theory of gravity and calculate what is the period of swinging of this planet. It's about 1 hour. Then you go into the movie and you see two waves. There's a wave that you see at the beginning of the period when the people are down there on the water planet, and a wave when they're leaving. And it's about 1 hour between the two waves. So everything fits together. And a physicist or a student, including a high school student who knows about gravity, can work the numbers out and everything fits together. There is another amazing thing, though, however. The orbit of Gargantua around the black hole is the same as the orbit of the Earth around the sun. And it's moving at basically the speed of light. And so the orbital period is 1.7 hours around the black hole. But because of this slowing of time, it appears to the people on the planet, on the water planet, that the orbital time is about 100 milliseconds. That is about 1/10,000th of a second to go around the black hole. Now, how can that be? It would seem they're moving faster than the speed of light. And the answer is, in fact, the spin of the black hole is dragging space into motion around the black hole. We call this the dragging of inertial frames. It's dragging space into motion so fast that, in fact, space is whirling around the black hole almost as fast as they are. And so even as seen by the people on the planet, they're going at less than the speed of light relative to inertial reference frames. So again, it's quite amazing, the effects of the slowing of time that you see here. It's not, and they are, from neither point of view are they going far faster than light. Okay, I've done some sort of complicated stuff. I want to pull back now for a while and do some fun stuff about this movie that is easier to understand. So let me begin by visualizing Gargantua and its disk. So Gargantua has a disk of hot gas around it, as shown here. Here is an IMAX camera that Christopher Nolan used. And the question is, what does we wanted to compute what this Gargantua looked like with its disk of hot gas by propagating light from this disk of hot gas that's sort of like the disk of hot gas that's sort of like the rings of Saturn. And so a light ray emitted off the back face of this disk goes up and over the black hole and down to the camera like that. But another light ray that is emitted from this location goes up and over and down to the camera on almost identically the same path, even though they begin far apart. That's because of the tidal forces, the stretching of things. And that stretching basically stretches the space between these two light rays. And so when the people I was working with at DNEG, the double negative visual effects, started to try to make images of what this would look like, they couldn't do it because the light rays began quite far apart to produce something that is separated by less than 1 pixel at the camera. And it was a mess. And so we had to develop a whole new way to do this imaging. And what we did was we propagated light beams instead of light rays, overlapping light beams. And we built a visualization scheme based on this, which we then published in a scientific journal. And that paper in that scientific journal, it's one of the 2 most popular among scientists journals for technical things about relativity. That paper is by far the most downloaded paper in the history of the journal. Not because physicists are downloading it, but because people interested in the whole issue of how these movies were made have been downloading it. And so this is the reference to that. And so in the end, we propagated 26 million overlapping light beams to the camera in order to make the images that you see in the movie. Now, the disc that we chose to do, we made it be hot, but at a temperature about the same as the temperature of the sun. So what it would actually look like, according to the calculations we did, if you ignored the fact that this side of the disk is moving toward us, and so it's shifted to the blue, and that side of the disk is moving away, it's shifted to the red, it would look like this. And Christopher Nolan looked at that, and he said, we can't use that in the movie. The audience will be completely confused by this thing. It's just too complicated. He said, so I'm going to slow down the spin of the black hole in order to make the image be more symmetrical around it. So he slowed the disk down, and he said, as is done here, that I'm going to leave off this Doppler shift where that side of the disk is moving toward us and that side away, so this should be blue and that should be red. And I said, you can't do that. I mean, that's the way it really is. And he said to me, not to a human eye. When light is really bright, the human eye cannot distinguish colors very well, and it cannot distinguish intensities very well. And we're imagining this as a human eye seeing this, and so we're going to leave that out. So he tried to be realistic as he could, up to the point of even dealing with the limitations of the human eye. So this is the image that we wound up with in the end. It's the Interstellar's iconic black hole image. And now let's explain this image. So if you have then a light ray emitted off the back upper face of the disk, it goes up over the black hole, pulled by the black hole's gravity, down to the camera there. So it's coming down from above. And so that makes this part of the image, the image of the top back of the disk. And a light ray coming off the bottom back face of the disk comes up to the camera, and so that makes this piece. And the light ray from the front of the disk goes directly to the camera and makes the crossbar. So that's a very simple explanation. I guess it was 5 years after the movie came out, astronomers succeeded for the first time in actually making an image, a photograph, of the gas around a black hole. It was the gas around the black hole in a galaxy called M87, a very, very massive black hole, even heavier than the one in Gargantua. And they did this by combining the data from radio telescopes all over the world, at all these locations on the world, combining the data from those by what we call coherent techniques. So that it was as though you had a radio telescope that was the size of the Earth itself. And they actually worked with 1.3 millimeter wavelength light for this purpose. And this is the image that they got. It's basically a photograph. And many people said, gee, that looks a lot like what you saw in Interstellar. I think it looks not at all like what we see in Interstellar. Here's Gargantua, and there's M87. And so I asked my friend Oliver James at the Double Negative Visual Effects House, who was the chief scientist there, is the chief scientist there, and he was took the lead in making the visual effects in the movie, to make a film clip that explains what the difference is. So he said, let's begin with our black hole with a camera near the equatorial plane of the black hole. And so you have an image that looks like that. And he said, then let's move the camera up to the North Pole of the black hole and see what happens. So you can probably guess what happens. You move up toward the North Pole of the black hole, and then you smear this out because the astronomers had very poor resolution. And there you are. Though with the Doppler shift present, so it's brighter on one side than on the other, and that's what we left out, as I said. That's actually not fully correct, because the gas around the black hole M87 is not in a disk. It's moving in a more three-dimensional way, but that is fundamentally, basically that's what is going on. Now, as you're all well aware, in this movie, there is a wormhole. And so this is a drawing of a wormhole reaching from the vicinity of Gargantua down to the vicinity of Saturn. And you remember Romilly in the movie, he explains the wormhole by taking a sheet of paper. So imagine that's the sheet of paper, and he pushes a pencil through it and says that's the wormhole. And so this is basically Romilly, a more sophisticated version of Romilly's explanation. Now, there's a severe problem with wormholes like this that you would travel through to get from our solar system to the vicinity of Gargantua. And that problem is that wormholes implode. And so if you are trying to send a particle of light, a photon, through the wormhole, when it gets halfway through, the wormhole has imploded and squeezed off and killed the photon, and the upper and lower parts of our universe are disconnected from each other. And this is an effect discovered by John Wheeler, my PhD advisor, a few years before I first met him, started working with him. So that was back in the 1950s, no, early 1960s. So the question then arose here, and also in the movie Contact, which Linda Opes did with Carl Sagan: how do you hold a wormhole open? And the answer, it turns out, that you need to fill it with what I would call exotic matter. And this is matter that will repel gravitationally. So these walls basically are repelled from each other by filling it with this matter that repels gravitationally. That means in order for it to repel gravitationally, it has to have negative mass or negative energy. Mass and energy are equivalent, according to Einstein. There's a fancy formula here I'm going to ignore, but what the fancy formula says, and this is a more precise statement of what's required to hold a wormhole open, that if you're moving through the wormhole at the speed of light, the average energy density that you see as you move through needs to be negative. Now, how is it possible to make exotic matter? I mean, that's wild to have matter that repels gravitationally. But the answer is yes, it is possible, and it has been done in the laboratory. It is done in the laboratory by physicists due to something called vacuum fluctuations. If you have a box and you remove everything from the box that you possibly can be removed, there still remains in there tiny random fluctuations of everything that ever could exist inside the box, including fluctuations of light, of X-rays, of radio waves, everything. And these vacuum fluctuations are responsible, in fact, for the fact that with this laser pointer that I have here, that the photons from the laser pointer, as they arrive at the screen, they arrive randomly. You don't see the individual photons, but if you have really good instrumentation, you discover that the photons are arriving in a random pattern at the screen, and that's caused by these vacuum fluctuations that are always present, beating against, working together with steady laser light. And working together, they produce these fluctuations. And so if you if one region of space borrows these fluctuations from another region, then the region that has loaned the fluctuations, it has less energy than the one that borrowed it. And it turns out that the vacuum fluctuations have no energy. Even if they're fluctuating, they have no net energy. They're just like a piece of the vacuum. So if one region borrows and the other lends, this material is then exotic. It repels gravitationally, and this piece attracts gravitationally. And I'm going to skip over this next slide, which is meant to give a specific example for how you can then use these vacuum fluctuations, perhaps to hold a wormhole open. There's been a lot of work done since the movie Contact came out, where where I helped Carl Sagan use vacuum fluctuations to hold a wormhole open. A lot of work has been done by physicists, and we don't have a final answer. Can you make enough exotic matter, put it inside a wormhole to hold it open so people could travel through? The answer is we don't know for sure. But the fact that we don't know for sure means I felt free to use wormholes in this movie, as we did also in Contact. So here is Interstellar's wormhole, and I made for the visual effects people a model of the wormhole with 3 parameters: the length of the throat here, how fast it opened up there, and the radius or circumference of the throat. And Oliver James, the chief scientist at the Visual Effects House, he then incorporated that into a computer program that he was propagating these light beams through the wormhole. And Eugenie von Tunzelmann and her artistic team at this visual effects company, they made paintings that correspond to the nebulae and the black hole on the other side of the wormhole. And then we propagated the light through the wormhole to produce images. And so this was and then we gave Christopher Nolan the images that corresponded to a particular shape and size of the wormhole. And Chris picked this for the shape of the wormhole because it produced that for the image. If you looked into the wormhole, you're looking through our mouth of the wormhole and out the other mouth to the vicinity of Gargantua. And so this is what you see in the movie because of the particular paintings that the artist drew for what was going on down here and the shape of the wormhole that Chris had chosen. And so the discussion of that is all in a scientific paper, again, a widely downloaded scientific paper where, in this case, students are invited to do their own light propagation through the wormhole and build images like this, but not with the high resolution required for an IMAX film. And so once that had been worked out, then Chris said, okay, we want to go through the wormhole. Send me a movie of what it looks like to go through this wormhole. And so the team at DNAG in London, they took their camera and they carried it through the wormhole and computed a film clip of what it looked like to go through the wormhole, and this is what they got. So this is you were not going to find this anywhere on the web. This is what it gives. And so, let me just pause it for a moment. Sorry. Come on. So let me just remark, this is Saturn. The wormhole mouth is much closer to us than the planet Saturn, so it looks like it's nearly as big as Saturn is. It's really only about 2 kilometers across. But because it's much closer, it looks about the same size. And light from Saturn goes around this side of the wormhole, and it produces this image, distorted. Light going around the other side of the wormhole gets distorted into this very, very banana-shaped image. So that's 2 images of Saturn. And so we now are traveling through the wormhole. We're just about to enter the wormhole mouth. It's very exciting. Here we go. We're entering the wormhole mouth. We're traveling through, and we're now on the other side. Having seen this, Christopher Nolan telephoned me. He said, "Kip, we have a problem. Would you come over to my house?" And I said, "Sure." So I drove over to his house, and he played this movie for me, and he said, "It's not exciting enough. What do we do?" And I told him, "This is the one place where I think we both agree you use your artistic license." And so he then combined this with some other trips through wormholes that had different shapes, and he added on some sound. And this is what you see in the movie. What you see in the movie that I'm going to show you, this film clip, is the absolute truth until Cooper pushes the joystick to go plunge into the wormhole, and then it's modified by artistic license, as we say.
We're ready to say goodbye to our solar system, to our galaxy. Here we go.
And this is where he has changed it. That was much more exciting, but that's, as I say, the one place in the movie that does not correspond to what the real science says. Now, I'm moving toward the end of this discussion, and I'm headed toward discussing the end of the movie. Which, let me ask, who in this audience understood the end of the movie? Before reading the book, if you've not read. Okay, so Chris and I had long discussions about the end of the movie, and very, very early on, he said to me, "I want to have an ending for this movie that is as puzzling, as hard to understand as the end of the movie 2001: A Space Odyssey, Stanley Kubrick's masterpiece." So I said, "Great, that's your right to decide that." As we got through sort of conceiving the end of the movie, and then he was actually nearly through, it was beginning to do his filming, and I was beginning to think about writing this book. He said, "You can explain the end of the movie in your book, and I'm not going to explain it anywhere." So in fact, it is only in my book that you'll find the explanation. The explanation has to do with the 5th dimension that I talked about before. Our universe has 3 dimensions, east, west, north, south, which I draw here, but I don't draw up, down. Instead, I've removed one of our space dimensions, and we keep time. But the 5th dimension, as I told you, which we call out, back, goes away from our universe. And that's the 5th dimension. And now there's a problem with gravity if you have 4 space dimensions in one time, which is what you have here. And if space is not warped, then you have the problem that if you have a source of gravity here, the gravitational pull, the gravitational field, I think of this as a field of arrows that indicate the direction of pull of gravity. Gravity can spread out in 3 dimensions inside our universe, inside our brain, as you call it. But there's a 4th dimension going into the bulk that gravity can spread. And because it can spread out in 4 space dimensions, it turns out the gravitational pull changes as 1 over the cube of the distance from the source of gravity. But that's not what we see. We measure 1 over the square of the distance from the so-called Newton's inverse square law. And so this cannot be what our universe is like. It was Lisa Randall and Raman Sundram, 2 colleagues of mine, who understood how nature solves this if there really is a 5th dimension, a 4th space dimension, a 5th dimension. And that is that the space surrounding our universe, our brain as we call it, brain is short for membrane, space around it is so warped so badly that if I move up perpendicular to our universe, out of our universe, into the bulk, and you, say, move up perpendicular into the bulk, and if we're initially separated by 1 kilometer, when we've gone up by 1/10 of a millimeter, we're separated by 100 meters. If we go up another 1/10 of a millimeter, we're separated by 10 meters. Another 1/10 of a millimeter, we're separated by 1 meter. So there's just not very much space up there. This enormous squeezing of space occurs, they postulated, and there was some rather good reasons why that might be the case that I won't go into. And this is called anti-de Sitter space, or ADS5 is a technical phrase. But they argued, and I think it's very plausible, that if there is an additional space dimension, that's the way that space dimension behaves. And because there's so little space up there, the gravitational field lines, the force lines of gravity, get bent horizontal very quickly as you move up into the bulk, and you recover this inverse square law as opposed to inverse cube law. But the trouble with this is that there's not enough space in the bulk for science fiction action. And so I solved that by making this be a finite distance over which space is warped. Then there's another brain, like our universe up there, which we call a confining brain, and another one down here. And they hold in here a sandwich of this highly warped space, and above there, it's just flat. It's just ordinary space above there. So our universe actually comes in a very thin structure with 2 accompanying universes that are helping to hold in this weird warping of space. So there's a mathematical model for this, and this mathematical model underlies the entire movie. And so then in 2006, I had a conversation with Lisa Randall, who had conceived this idea. She's a professor at Harvard. And she said, well, I've got good news and bad news. The good news is that this model for our universe was actually invented previously by Ruth Gregory in Britain and Valery Rubikov and Sergei Sibiryakov in Russia. The bad news is that Ed Witten and others among our physicist colleagues showed that this model for our universe is unstable, that the confining brains will come crashing down and hit our brain and destroy our whole universe if that's what the universe is like. Nevertheless, this is the model under which that underlies the movie Interstellar. And it is Professor Brand's job to figure out how this universe is stabilized. How do we save our universe from being destroyed by 2 other universes crashing into it? This is not in the movie at all. Well, it is in the movie, in fact, as I will explain in a moment. But this is connected then to the gravitational anomalies that you see in the movie. You recall that there's a dust storm in the movie, and the dust falls in a pattern on Murph's floor, a pattern of dust that is a long stream of dust that actually turns out to be a Morse code that is telling them where to go to find the remnants of the NASA. But Cooper then sees that, and he does an experiment. He tosses a coin, and the coin falls on one of the long stripes. And he tosses it again. It always falls on a long stripe. Always. Come on. Sorry. So and this is a gravitational anomaly that has to be understood, and he has other gravitational anomalies in the movie. And so Professor Brand struggles to understand the anomalies, along with Murphy Cooper, Cooper's daughter, now grown up to be in her 20s or about 30 years old. And they're struggling in order to save humanity from a dying Earth. And I won't, if you wish, in the discussion later, we can discuss what is really going on in this dying Earth. Which, you do see that in the film that it's a dying Earth and people need to be rescued by going up into space. So they want to save humanity from a dying Earth. And Professor Brand has a plan. He wants to manipulate the gravitational anomalies in such a way that with the meager rocket power that they have, they can launch colonies into space in cylindrical spacecraft like that and lift the remnants of human civilization up into space. The problem is they don't have enough rocket power to do that against the Earth's strong gravitational pull. But he knows there are gravitational anomalies. There's something up in the bulk, in the fifth dimension, that is controlling gravity and capable of making gravity behave quite differently than what you normally see. And so, in fact, he hopes that he can find some way to reduce the strength of gravity near the Earth for a few hours. And thereby, during those few hours, relatively weak rocket engines can lift the remnants of humanity up into space. So that's his goal. And how is he going to do that? Well, Murphy remarks that we have half the answer on the blackboards in his office. And he's been struggling, the two of them have been struggling together. Professor Brand and Murphy Cooper have been struggling together for quite a while to figure this out. There are actually 16 blackboards. You can go to that location on the web and you can see all 16 blackboards. And the other half of the answer is embedded in the professor's equation, and they're trying to solve the professor's equation in order to learn, get the other half of the answer for how to control gravity and turn it off. And they speculate that if they can make measurements of the properties of gravity near the singularity inside a black hole, inside of Gargantua, that will teach them the missing information about how gravity behaves up in the fifth dimension and how to do what they need in order to save humanity. So this is basically what's going on in the backstory of this film. And so here's the professor's equation. It's on one of those blackboards that you see in those scenes in the movie. And it's called my equation for the effective action. And then this equation is something that Brand and Cooper, Brand and Murphy Cooper have been speculating about, but they aren't sure of the equation. They're trying to get the correct form of the equation is what they're trying to get at. This has a technical name. It's a classical limit of a quantum effective action, and it means nothing to 99% of you, and there may be one person who may know a little bit about this. There may be a few more people. But that is the backstory. And the entire backstory is on these 16 blackboards, which you can go look at on the web if you have a strong physics background and see just what they're thinking about. So the movie's ending. Where are they going to learn the quantum effective action? From a singularity down inside Gargantua. There's a singularity that's highly chaotic, where they will undoubtedly die if they go in there. There are two other singularities. One is an infalling singularity created by everything that falls into the black hole after Cooper and TARS, the robot, go into the black hole. Everything that falls in afterwards, time is so screwed up inside the black hole, and this is true, that it falls in, is seen inside the black hole in a fraction of a second. It's a huge shock wave flying in. And then everything that fell into the black hole before Cooper goes in is scattered back, a little bit is scattered back and makes a much weaker outflying shock wave or shock singularity. And these are the gentle singularities that are discussed in the movie by Romilly, the theoretical physicist that's on this mission. And so we see then Cooper plunge into Gargantua.
Approaching the event horizon. Port side, dipping down beneath it.
So he's inside the black hole. But you still see the universe up above him because light can come in from outside the black hole. Light just can't get out from inside. So you still see the universe above him. He goes in and he encounters this weak outflying shock singularity. If you look carefully, just at the last moment, you see the Ranger spacecraft torn apart by tidal forces. You see Cooper thrown out of there, and he is, and this part is not shown, he is captured by a tesseract, which is a spacecraft that travels in the higher dimension in the bulk, a spacecraft that bulk beings, a civilization that lives in the bulk, has created. And it is a four-dimensional cube. He's captured in the three-dimensional face of this four-dimensional cube. And this spacecraft carries him up out of our brain into the bulk. He can't go back through the horizon. Nothing can get out through the horizon, but he goes up out of our brain into the bulk, and he travels across the bulk. Here he is in one of the faces of this four-dimensional cube, this tesseract, traveling across. That's our brain down there. The distance up here back to Earth is quite a bit less than the distance between the Earth and the Sun, so he can get back in a matter of a few minutes. Whereas down in our universe, down in our brain, the distance is billions of light years. So he gets back by going up here where the distance is just ever so much shorter. Again, this is all based on general relativity, in this case in 5 dimensions. Notice S, there's a little bit of speculation here. Well, more than a little bit. The tesseract then docks by Murph's bedroom. And so here he is. This is the bulk coming out of here. I've removed the attempt to show the 3 dimensions of the tesseract. I'm showing it as though it's an ordinary cube. Here he is in one face of the cube. There's Murph in her bedroom in the other face of the cube. And it's actually docked right there. You don't see it if you are in our universe because that tesseract is in the bulk, in the higher dimension. So there's no way for you to see it, no way for Murph to see it. And if he looks up, he sees light coming from Murph that has gone through his face of the tesseract, through this face, and up from her through that face, her face across the top face and down. If he looks to the side, he sees light, a picture of Murph. If he looks to this side, he sees a picture of Murph. In any direction he looks, he sees Murph. Again, this is well-established physics. The idea that this 5th dimension exists is speculation. But if you accept that it exists, then this is the way things would work. Nolan then complexifies the tesseract to some degree. So here you see her bedroom above and below and on the sides, on all sides. But you see some strange things that he calls extrusions, which I discuss at some length in my book. And here is Cooper. When you first see him in this strange structure, he's kicking and screaming, and the tesseract is moving back to Earth. And by the time he is calmed down, it's back at Earth, and you see the images of his daughter in her bedroom at these various locations. Cooper then has learned the missing equation. He's learned about the quantum effective action for gravity in 5 dimensions. He has the secret of what Murph needs in order to save humanity. And he just has to send the information back to her. And so he does so by pushing on the extrusions, and you see him pushing on one of these extrusions, sending gravitational signals through the bulk and backward in time to Murph. Cooper never himself goes backward in time, but the tesseract is part of the bulk, and it has backward time travel in its interior. He's only in a face of the tesseract. He doesn't experience it. But the gravitational signals go through the interior of the tesseract, and they go backward in time to give Murph that information that she needs in order to save humanity. And at the end of my book, there's a technical note that shows the structure of space-time inside the tesseract for anybody who wants to go there and try to figure this out. But again, there's a precise mathematical model based on general relativity in 5 dimensions underlying all of this. So he tells Murph the quantum effective action, the professor's equation. She uses it to control gravitational anomalies by reducing the Earth's gravity for a few hours to save the remains of humanity. And there you have it. They're saved. And that's the end of the movie. Thank you.